Hey there, space explorers. Welcome to another deep dive, and this time we're taking on a real head-scratcher. We're talking about the James Webb Space Telescope.
The JWST.
Yeah, that one. I mean, those images we're getting, come on. Absolutely mind-blowing, but
Oh, yeah.
it's not just the pretty pictures, though, right?
Right. It's the data.
It's the data. That's what has scientists really buzzing.
Yeah.
And maybe a little bit concerned, too, right?
A little bit.
Because it's really challenging some of what we thought we knew about the universe.
It really is. And I think what's so fascinating for me about the JWST is it's showing us that the universe might be expanding faster. Way faster than we ever thought.
Okay, so rewind for a sec, because not all of us are astrophysicists here, right?
Yeah.
We know the universe is expanding, right?
Yeah.
Like a balloon.
Yeah. Expanding like a balloon.
You blow it up, it gets bigger.
Yeah.
And the rate of that expansion, scientists have a very fancy term for it.
Right.
They call it the Hubble constant.
That's right.
Sounds simple enough.
It does sound simple.
But hold on to your hats, everyone, because this is where things get really interesting.
This is where the fun begins.
And by fun, you mean kind of like scary and confusing.
Yeah.
Like, what's going on in my closet when I close the door?
Possibly.
So we have these like incredibly precise ways of measuring the Hubble constant
Right.
two different ways.
Yeah.
And they are giving us wildly different answers.
That's right. And it's almost like you have two different tape measures.
Okay.
And you're measuring your living room, and one is saying it's 10 feet longer than the other. So something is not adding up.
That's a big difference.
Yeah, big difference, yeah.
Okay, so walk me through this.
Okay.
What are these two methods? Why are they giving us such different results?
Well, so one of the methods uses the Planck satellite.
Okay.
And I always think it's really interesting, because imagine looking at the universe's baby picture.
Okay.
And that's what Planck is doing. It's analyzing the afterglow of the Big Bang.
Wait, you can actually see
You can see remnants.
remnants of the Big Bang.
Yes.
That's incredible.
It is pretty amazing.
That's so cool.
And that gives us clues about how the early universe was and how fast it was expanding back then. And those measurements from that very, very early universe are tied to something called the Standard Model of Cosmology.
Okay, another fancy term.
It's a very fancy term, but it's basically our master recipe book for the universe. It explains all the ingredients, like dark matter, dark energy,
Yep.
how they interact with each other.
Gotcha. So this Planck satellite
Yeah.
is giving us one measurement.
One measurement based on that very early picture of the universe.
Yeah. What's the other method?
So that's where JWST comes in,
Okay.
and it relies on these really cool stars called Cepheid variables.
Cepheid variables.
Cepheid variables, they're special because they pulsate,
They do.
and their brightness is directly related to how fast they're pulsing.
Okay.
So it's like a cosmic lighthouse.
Oh, that's cool. I like it.
They have these beams that are visible across these vast distances.
So we use these Cepheid variables to basically track how fast the universe is expanding now.
Exactly, and you're comparing it with how fast it was expanding back then.
And it's different.
It's different, yeah.
And not just like a little bit different.
So the difference between those two measurements is about 10%.
10%
10%. Now, that may not seem like a lot.
to the average Joe.
Yeah, but in the grand scheme of the universe, that's a lot. That's huge. It's like finding out that your house is 10% bigger than you thought.
That would make me question a lot of things, I
Yeah,
think.
you'd start questioning everything, wouldn't you?
Like, how much is my mortgage?
Exactly.
Okay, my mind is officially blown to incredibly precise measurements,
Right.
both based on, like, solid science,
Yeah.
and they're telling us totally different stories about how fast the universe is expanding.
I know. And that's what's so interesting.
That's a space enthusiast to think.
I know. Well, that's the million-dollar question, right?
Great.
And this is where things get really interesting, because this discrepancy, scientists are calling it the Hubble tension.
Okay.
It throws a wrench into everything.
So it's not just which measurement is right.
Right.
It's what does this mean about, like, our whole understanding of
It's
the
not
universe
term.
as a whole.
It really makes you think about the universe in a whole new way. And remember that Standard Model of Cosmology.
Oh, yeah, our recipe book.
Yeah, our master recipe book for the universe.
It's got it all figured out, right?
Well, we thought it did. I mean, it's
Yeah.
been so successful
Yeah.
at explaining all these cosmic mysteries.
Uh-huh.
But this Hubble tension is suggesting that maybe, just maybe, we're missing an ingredient or two.
Okay.
Or maybe we need to rethink the entire recipe altogether.
Okay. Now you're making me hungry and a little bit nervous.
A little bit of both.
So what could these missing ingredients be? What kind of cosmic surprises are we talking about?
Well, for starters, there could be new particles out there
Okay.
that we haven't even discovered yet.
Oh, wow.
Particles that interact with the universe in ways that right now we can't even imagine.
Okay.
Or maybe, just maybe,
Hit me with it.
our understanding of the fundamental forces of the universe.
Okay.
Gravity, electromagnetism, all that good stuff.
Yeah.
Maybe it needs a serious update.
Wait, are you saying like rewrite the laws of physics?
I mean, it's not entirely out of the question. This discrepancy could be a sign that there's something fundamentally different about the way gravity works on a cosmic scale
Okay.
than what we observe here on Earth.
Okay.
Or it could point to entirely new physics that we haven't even begun to explore.
See, this is blowing my mind because I always thought physics was like,
Set in stone.
yeah,
Yeah.
like we figured it out.
Right.
You know, like Newton and everybody else was like, boom, nailed it.
Exactly. And that's the beauty of science, though.
Okay.
It's like just when we think we have it all figured out,
Yeah,
the universe throws us a curveball,
it does.
like the Hubble tension.
Yeah.
And it reminds us just how much more there is to learn.
Okay.
And believe me, scientists are like diving headfirst into this mystery.
Yeah.
They're so eager to try to unravel these secrets.
So what's next in this whole like cosmic detective story?
Yeah.
What are people doing to try to solve this case of the misbehaving Hubble constant?
Well, for one, JWST is going to continue to play a starring role. Remember those Cepheid variable stars?
For little lighthouses?
Yes. Astronomers are planning to observe even more of them
Okay.
at even greater distances
Oh, wow.
to see if this faster expansion rate holds up across the entire observable universe.
So it's like they're trying to get a wider view of the
Yeah.
universe's expansion.
Exactly. Like if that 10% difference in your house,
Yeah.
is it consistent in every room?
Right.
Or is your basement suddenly like twice the size? And at the same time, the JWST is out there collecting more data.
Yeah.
The theoretical physicists, they're hard at work too.
Okay.
They're like cosmic detectives, right?
Yeah.
Combing through all the evidence, trying to crack the case.
So what are they looking for?
Right. What could explain this faster than expected
Yeah.
expansion? Well, some physicists are revisiting old theories,
Okay.
dusting them off, seeing if maybe they hold some missing clue.
Okay.
Others are proposing radical new ideas.
Like what?
Ideas that could like completely revolutionize how we understand the cosmos.
Okay.
They're looking into things like modifications to Einstein's theory of gravity,
Oh, wow.
the existence of new fundamental forces,
Okay.
and even the possibility that our universe is just one of many universes,
A multiverse.
a multiverse.
Okay, now we're getting really trippy.
Yeah.
So this isn't just like
Well,
tweaking the numbers a little bit. This
yeah.
is like fundamental changes in how we view like,
It's like realizing the Earth isn't flat.
yeah,
know,
yeah.
It's a paradigm shift.
And who knows what we're going to find when we like really start digging into this stuff.
Exactly. Isn't it amazing, though?
Yeah.
The universe is full of wonders,
Yeah.
mysteries, waiting to be unraveled.
The mystery.
And this Hubble pension, it's just one piece of the puzzle,
Yeah.
but it's a piece that has the potential to change everything.
I got to say, this whole deep dive has been incredible.
It's been fun, right?
Yeah, we started with like
Yeah.
these stunning images from like
The most powerful telescope
the most powerful telescope ever built.
ever.
And now we're questioning like the fabric of reality.
Exactly.
It's amazing.
We've stepped through a portal into the unknown.
That's a great way to put it.
Right.
And, you know, I'm feeling very small, but also kind of excited,
Of course.
you know?
You should be.
And like how much is out there that we don't know?
I know. And think about how much there is to still be discovered.
Exactly. And like we're just starting to
We're just scratching the surface.
scratch the surface. Well, on that note of cosmic wonder,
Yes.
this has been our deep dive
Hubble
on
tension.
a Hubble tension.
Everybody's talking about it.
But before you go, we want to leave you with something to ponder.
Okay.
We've talked a lot about dark matter
Yeah?
and how it influences the universe's expansion.
Right.
But what if this Hubble tension
Yes.
is telling us something totally new about dark matter itself?
Ooh.
Like, what if it's even weirder,
Yeah.
even more mysterious than we ever imagined?
That's a great question for everybody to think about.
Yeah, so keep those questions swirling
Yes.
as you continue your own exploration of the cosmos.
The universe is out there waiting.
Until next time, everybody keep looking up.